Hello, everybody. I am Mehmet Duray from Süleyman Demirel University in Turkey. I am a partner of the project that name is Clinical Care for Electrical Stimulation in Physiotherapy and Rehabilitation. Our project was founded by the Erasmus Plus program of the European Union. Our project coordinator is Pamukkale University and other partners are University of Craiova, Hatay Mustafa Kemal University, Başkent University, Süleyman Demirel University, Şule University of Applied Science, and Burdur Mehmet Akif Ersoy University. And we have also association partners that are Turkish, Romanian, Lithuanian, and Estonian Association of Physiotherapists. I will tell about denervated muscle physiology in this presentation in the under the model 1 health and denervated muscle physiology. I work with uh, Gökhan Bayrak from Muş Alparslan University. I want to thank to him his special contribution. Denervation is a spatial condition and is a spatial process develops due to central or peripheral nervous system damage. And this denervation process causes to especially loss of voluntary and reflex muscle activity. And these, due to these loss activity, the muscle atrophy and some change in muscle stability are seen. The denervation process and denervation varies to some factors. These factors can be type of injury, the age of patient, or the distance between the lesion area and the cell body. Uh, these factors cause to decreased or increased recovery time. If the reinnervation after the injury is not achieved in the first year, or the reinnervation process is delayed too long, substantial atrophy and permanent loss of function can be observed. These are very negative consequences, and but sometimes they can be seen. So after denervation, not only loss of muscle contractile function is seen, but also trophic, mechanical, and molecular change occur. The denervation process is divided three phases. In the first phase, the rapid loss of muscle function, reduction in muscle mass, and atrophy of muscle fibers begins. After first pass, the second stage initiates, and the sarcoma organization begins to disrupt, and the muscle atrophy increase. In the last stage of the muscle denervation, deteriorated tissue articular, and the process in which interstitial fibrosis and adipose are dominant in the tissue begins. Some membrane changes in the denervated muscle are seen. We know that the healthy muscle fiber has the healthy muscle fiber cell membrane potential is about 80 millivolt under zero. In the denervation process, these resting membrane potential increase. It begins to be more positive. After denervation, myoclonic and neuromyotonic discharges, muscle cramps, and fasciculations may develop due to the impairment neural input between the neuronal system and muscle. The first signs of denervation is appearances of spontaneous fibrillation in the muscle. These spontaneous fibrillation is associated with the spread of acetylcholine receptors along to the muscle membrane from the early post-denervation period, and also the deterioration in the general structure of sarcoplasmic reticulum. I said that in the previous slide, the membrane potential after denervation or in denervation process becomes more positive due to the sodium ion flow to the cell membrane. And spontaneous action potential occurs when the resting membrane potential in denervated muscle and the resting action potentials reach to 60 millivolt under zero. And some cellular changes are seen in the denervation process. The first change is related with the mitochondrial activity. After the denervation, a complex plastic pattern initiates in the muscle, and these plasticity, cellular plasticity, affect the mitochondria. Firstly, slow-twitch oxidative type 1 muscle fibers transform to fast-twitch glycolytic type 2 muscle fibers. These mean the muscle lost the oxidative muscle fiber and the glycolytic muscle fiber increase in the muscle, and greater dependence on the anaerobic metabolism is seen in the muscle. This change causes to decrease in the number of intercellular mitochondria, and their complex structural anatomy deteriorates and begins to exhibit a more primitive and simple structure. Second, cellular change is related with nutritional functions. Glucose metabolism increase after denervation, and atrophic muscle fiber in this process. New atrophic muscle fibers don't contain glycogen or RRA, don't show acid phosphatase activity, and succinate dehydrogenase activity is very, very low. But it is more to after 28 days of denervation, two major changes are seen in different muscle fibers. In slow twitch skeletal muscle fibers, the insulin resistance appeared, and in fast twitch muscle fibers, insulin sensitivity is appeared. These changes are very, very harmful for the muscle, and other changes will be seen in lysosomal activities after denervation, increased activity of autophagy lysosomal system is a have a destruction effect on the proteins in the muscle. And in terms of change in the muscle tissue level, the major change is muscle atrophy. Muscle atrophy is related with the loss or interrupted connection between central or peripheral nervous system and muscle. After denervation, the atrophy process begins very rapidly because the muscle size is dependent to the signals from the peripheral nervous system or central nervous system. The muscle lost this stimuli stimulus connection, and after atrophy, the muscles the muscle have fibrous connective tissue in content and adipose tissue. The fibrous connective tissue and adipose tissue take the place of functional muscle tissue later on, and functionality of the muscle is lost timely. While in the first stage of the atrophy, the sarcomeric structure is protected. In the second stage of the atrophy, this sarcomeric structure is disrupted. Actin and myosin myofilaments, loss and disruption in myofibrillar alignment are observed. Subsequently, the size and number of the muscle cells declines significantly, or orientation of the sarcoplasmic reticulum system is disrupted, and the number of capillaries associated with the muscle declines too. We know that we talk about that losses in the nerve strength innervated the muscle are observed too. You can see the atrophic muscle in figure 1. Following denervation, firstly, increase in stem cell proliferation appears in the muscle, but as the denervation periods increases, the number of stem cells in the muscle tends to decrease over time. Depending on the severity of injury, the functional loss seen in various degree, and it shouldn't be forgotten that the atrophy is not related only with the denervation, but also it can be related with aging or disuse atrophy. After atrophy, the fibrosis can be observed in the final stage. We talk about these, and the muscle tissue is replaced by fibrosis and adipose tissue. Up to 4 months after denervation, the health muscle volume decrease to the 20%, 20%, and in 2 years after denervation, irreversible muscle fibrosis and fat infiltration occur. This means in the muscle, some harmful changes occur, and the mm, functional activity can't reverse again. Due to the denervation atrophy, the length of the fibrous tissue that replaces the muscle fibers tends to continue to shorten in the subsequent period. And all of these explain the contractures mechanism in the muscle in denervation process. Degeneration in the muscle is also characterized with fatty infiltration and accumulation. Muscle degeneration can be quantitatively evaluated as follows: grade 1, grade 2, and grade 3. In grade 1, a normal muscle with fatty infiltration of 10% of the cross-sectional area of the muscle is seen. In grade 2, this ratio increase and can reach to 50%, and last grade, in grade 3, the severe muscle degeneration is seen, and this ratio increase over the 50%. In degeneration process, some genetic factors are responsible. Some gen expression are seen, and this change begin to be seen as well as biochemical and physiological processes. The role of genetic factors can be divided 4 phases, and this process starts in the first 30 minutes and lasts 28 day of the degeneration. The fourth phase is oxidative stress phase, the second phase inflammation phase, third phase atrophy phase, and the last phase atrophic fibrous phase. In oxidative stage phase, Stochrome P450 enzymes provide the conversion of toxic metabolites into peroxygen radicals, and this is responsible from the muscle atrophy. In inflammation stage, some genes such as TNF, transcription activator phosphorylated by the genus kinase enzyme, or TGF-beta, and not-like genes trigger the inflammatory response. After inflammation, the atrophy stage begins under the influence of upregulated genes, and in this stage, especially proteolysis occurs with the activation of the destructive enzyme. After atrophy stage, the fibrosis stage started, and while cyclic adenosine monophosphate and extracellular matrix synthesis exacerbated denervated muscle fibrosis, increased ribosomal activity, supports enzyme activity that plays a role in collagenation. With Associate Professor Gökhan Bayrak, we want to create a table to understand or compare the denervation process with the healthy muscle, and we divided the denervation process as acute and chronic phase. In acute phase of the denervation, axonal growth activity decrease, but in the chronic phase, the axonal growth activity uh, more decreased. Atrophy begins, but in chronic term, we will encounter with the further atrophy. Infiltration of fat and spontaneous activity begins in the acute period, but they increase in the chronic phase. Muscle cell activity, muscle cell weight begins to decrease in acute period. The cross-section area of the muscle begins to smaller, and these increase in chronic period after 3 months. Sensory input and motor input from the nervous system declines and increase over time. You can see, as you can see in the table, and chronexy start the increase in acute period, but it can reach 4 millisecond in the chronic period. You can compare the denervated muscle characteristics with the healthy muscle characteristics, and you can reach more information from these references. This is our project team. I want to talk everybody separately for the collaboration. Thank you for listening.